Okay. Yes. So what happens when we have something like a tricopter or a bicopter? Okay. So in a bicopter or a tricopter, you have only fewer than four. So let's say uh, let's say two of these propellers move clockwise, and one of them move out anti-clockwise. So what will happen? The propeller that is moving clockwise. Let me change the color. Okay. Uh, will so the motor of that propeller will turn the propeller clockwise. So it is applying a clockwise torque. But then the propeller, by Newton's third law, will apply a counterclockwise torque on the motor, which is rigidly attached to the frame. So the frame of the quad rotor or of the VTOL vehicle will experience the torque in the opposite direction of the rotation of the propeller. Right? So let's say that tricopters, these two propellers which are rotating in clockwise direction will apply a counterclockwise torque on the frame, right? Whereas this one will apply a clockwise torque on the frame. So just by turning on the motors, we are experiencing a net moment on the frame. Assuming that all the motors are spinning at the constant velocity, we were expecting it to either move upwards or hover or come down, right? Because depending on whether it is balancing the weight or not. But this will start spinning, right? Dep- So we also need to control the RPM of these propellers, right? So that the yaw will get balanced, right? And so if so, we are actually the RPM is the yaw is also contributing to the yaw. It is also contributing to the at what height we have to balance the drone. So it becomes like the more degrees of freedoms are there, but our controls are less. Okay, and it is true with the quad rotor also, but somehow we can decouple the hovering mode and the roll, pitch, and yaw. Okay, so the hovering, if you just want to hover, then in the hovering position we will not get roll, pitch, and yaw. So it is possible, but in case of bicopter, it's tougher. Okay, so for example, in quad rotor also, if you want to move in x direction, then we have to pitch. There is no other option. Okay, so there is coupling, but then here the for bicopter and tricopter the coupling is much higher, where as a result it is very difficult to control its degrees of freedom independently. Okay, so that is why quad rotor is the least number of, let's say, propellers that is required to control it, in an efficient way, or in a let's say in a comfortable way, or in a way which is good for an to have any application to be helpful any task. Okay, so that is, I think that much is enough, more than enough for the discussion. So let's say that the answer is hexacopter because it has six propellers, but it is very interesting, to have uh, to decide what configuration to use for a particular application or something like that. Okay, so for example, even for a quad rotor, let's say one of the rotor fails, then it becomes something like a tricopter. So it is interesting to learn algorithms for tricopter and even bicopter because uh, uh, so that is the beauty of robotics or control systems. Okay, so this is for something like you can search like fault tolerant control of quad rotors, where you can have very nice videos online they cut the one of the propellers and still the quad rotor performs. So something in a something like a disaster scenario or something where one of the propellers gets damaged or something like that. Even then your quad rotor should try to complete its task. Okay, so that's why such research is important, and we need to study uh, these things. Okay, so let's move on to something that is more relevant to this course. If a physical point in three-dimensional space is expressed in terms of homogeneous coordinates, we want to change from one coordinate frame to another. We use a 4 cross 4 homogeneous matrix given as this, and what is R? So as you know, homogeneous matrix is a 4 cross 4 matrix. Okay, and in the context of robotics, this n transpose, eta transpose, sorry, is 0, and there is a 1 at the end, the sigma is 1, and this particular thing P is a position vector or the relative position between the two frames to which this T is relating. So I will talk about that also. So let's say this is X, Y, Z, and this is a rotation matrix. So rotation matrix, as you all know, is an orthogonal matrix. So what is an orthogonal matrix? Orthogonal matrix is R transpose is equal to R inverse. So the transpose and the inverse of the matrix are the same, right? Uh, and also you can see here that this transformation matrix is relating what? It is relating the mobile frame to the fixed frame. Okay, so and what is XYZ? XYZ is the the coordinates of mobile frame with respect to the fixed frame, or the coordinate of the next frame which is to the previous frame, and T is the homogeneous matrix relating these two frames. Okay, and R is the rotation matrix that relates PM to PF. Okay, frame M to frame F. Okay, uh, so let's move on to the next question. Okay, so this question is interesting. Okay, so we have been told that there are two frames, and what is the rotation matrix or the coordinate transformation matrix that relates F to M, F and M. Okay, so how do we find this? Okay, so before that, let's take a simpler example. Okay, let's take, so here if you see there are the M1 and F1 are at 90 degrees. Okay, and then M2 and F2 are also at 90 degrees, and M3, F3 are also 90 degrees. But can we, rotate, imagine a sequence of rotations so that this can be achieved? So let's say that we rotate the F1 to the F frame about F3, okay, by some angle, and to get M1. Okay, and so what will happen is that we will get F1 dash over here, and F2 will go over here. So F2 dash, right? And F3 will stay in place. So this is nothing but F3 dash, right? Now what we want is we have aligned M1 and F1. Okay, so is it possible to have one rotation that will align F3 dash with M3? So we want to move in this particular direction, and M and F2 dash with M2. So now we want to rotate, let's say, this way, right? So now we will have F3 dash aligned with M3 and F2 dash aligned with M2, right? So our first rotation and then you will get this orange frame, right? So our first rotation was about F3, right? And it was an anti-clockwise rotation, right? So it was an anti-clockwise rotation. So where is my cursor? Okay. So about F3 by, let's say, minus theta, or minus, sorry, we know the theta, right? So minus 90 degrees, we are rotating about F3. And afterwards, we are rotating about F2 again by clockwise. So first 90 degrees and then about F2. So this is 90 degree, minus 90 degree, and this is also minus 90 degree. All right. So let's try to, uh, find the matrix. So you know that, so there is this shortcut, not shortcut, you should have a trick to remember what are the rotation matrices for particular axis. Okay. So let's say that about F3 is what? Z axis. I assume it is also 1, 2, 3 means it will be X, Y, Z. Okay. So around F1, the rotation matrix, sorry, about F3, what will happen? The third column, third row will come 1 because it is the Z axis. Okay. Then we put zeros over there, and then cos always comes on the diagonal. Okay, for any standard XYZ axis, cos will always come in the diagonal, and on the off diagonal there will be sine, right? And where do we put the minus sign? We put the minus sign. So remember this. This is my trick to remember that always below the row which has 1, we'll put the minus sign. So below this there is nothing, so the first row will come, and we put the minus sign over there. So what is cos 90? 0, 0, minus 1, and 1. So this is the matrix for rotation about F3. Okay. So what is the matrix for rotation about? So okay, so this was minus cos. Okay, minus 90. Sorry for that. So minus 90 will be, this is plus 1 and this is minus 1. And then what is the rotation about F2? So it will be 1, 0, 0, 0, 0. Right, because the second row, second column is 2, right? So second row, second column will put 1. The rest of the 0, right? Is it right? No, it's not right. So let's go here. The same rows we have to put 0. Okay, same row and same column we have to put 0. And then as usual, cos of minus 90, cos of minus 90, sine of minus 90, sine of minus 90. And then where do we put the minus sign for the sine? So minus sign always comes with the sine, not with the cos. So below the row which has 1, so it will come here. Okay, and then we compute this, it will become cos 90 is 0, 0, 1, sine of minus 90 is minus 1, and this is plus 1. Okay, so this is it. And then we multiply these two matrices. So in which order do we multiply? So if this is a fixed frame, PF, okay, then there is a rotation matrix, and then there is PM. This is the frame that moved. Okay, and then the first rotation was what? About F3. So the first rotation gets multiplied to PM first. So remember like that. And so this will be 0, 1, 0, minus 1, 0, 0, 0, 0, 1. And then this is multiplied to 0, 0, minus 1, 0, 1, 0, 1, 0, 0. Okay. And let's go to MATLAB and just multiply this and see what is the answer. So let's make a section over here and let's multiply A3 for the rotation about A3 and okay, so let me just pull up the MATLAB screen. So it's 0, 1, 0, minus 1, 0, 0, 0, 1. So I'll explain how to do the multiplication in MATLAB. And some basics of MATLAB also, if time permits, we'll cover, or we can cover in the upcoming sessions also. That's not the primary requirement, but yeah, it's good to know. And then we want A2 to be multiplied to A3. Okay, A3 we are keeping on the right side because it is going to be multiplied first to the E3 because it was the uh, first rotation, right? Let's see what is the answer. Okay, so we get minus 1, minus 1, 1. So this kind of answer. So do not have that in the options. Okay, so either the options are wrong or we have made some error. Okay, so let's move to the another. I will show you a shortcut, more shortcut method. So basically, this is the way, like you figure out what are the rotations involved between two, and then you just get the rotation matrix and then you multiply among them. And let's go to the next method. Have I done some? Okay, there is this simple mistake. Uh, what? Wait a minute. So this is plus 1, 1, minus 1. And maybe I don't see any mistake. I think the options, there's issue with the options. Okay, so let's do by some other method. Okay, so this is more standard one. Okay, okay, so I forgot to load the PowerPoint. Yeah. Okay, so let's go back over here, and now what we can have here is we can have f1 dot m1, then we can have f1 dot m2 and f1 dot m3 and f2 dot m1, f2 dot m2, f2 dot m3, f3 dot m1, f3 dot m2, and f3 dot m3. And let's see what is the answer for this. So if you do by here, so f1 dot m1 is if f1 and m1 are in the same direction. No, they are not. So the dot product will be 0, right? F2, m2, are they in the same direction? No, they are not. So the dot product is 0. And F3, M3, are they in the same direction? No, they are not. So the dot product is 0. So what about F1 dot M2? F1 dot M2. So there is 90-degree angle between them, right? So that is also 0. Only F1 dot M3 is 1. Okay. What about F1, F2 dot M1? Yes, it is 1. What about F2 dot M3 is 0. So whatever gets aligned, right? Only for that will it is. So F3 is aligned with this particular direction. So there is 1 over here. Okay. So this is the answer. So earlier method that we performed, that is the more rudimentary way to do it, like to see. So that is more for the intuition. But here you can, directly apply formula between the two frames, right? But okay, so that particular method, maybe we have missed someone somewhere, but I think you get the gist. How, what is the logic? Okay, I think we messed up the rotation. So if we are rotating first about F3, then F2 dash will come here, F1 goes up, and then we rotate about F3. Yeah, so this, no, then we rotate about F2, so F2 will come here and F3 will go over there. Yeah, I think it's right. Okay, but then you get the gist. What are the two methods? And you can in exam, you should, I think, always you have less time, so you apply this method and this should work. Okay, so let's move on to the next question. And yeah, this formula is also given in the slides by sir. Okay, so a tooltip having a composite rotations of yaw pitch roll 30 degree, 45 degree, and 60 degree. Find the resultant compute the composite rotation matrix. So now since they haven't given any order, so we have to assume some order, right? Okay, so let's see. Okay, so one more thing that I have to clarify, that in this course, the yaw is taken about the x-axis and pitch is taken about the y-axis. Okay, and the roll is taken about z-axis. Usually in aerospace and robotics books, the x and z are reversed. Okay, yaw is usually taken about the z-axis, but uh, in this course, this is being followed. So you can, and then the first rotation. Okay, uh, so the rotation about z, as we know, is cos theta minus sin theta 1 0 0 0 0. Okay, and rotation about the y-axis is 0 0 0 0 cos theta minus, okay, so minus sin theta and plus sin theta. Okay, and rotation about the x-axis will be 1 0 0 0 0 cos theta minus sin theta. So you note that all the negative signs come below the row having 1. Okay, and you just multiply these three matrices. Okay, so the order that I follow here is, I will just pull up the MATLAB. Okay, so the order that I'm following over here, so this is question number 5, is the roll first, then pitch, and then yaw. Sorry, the yaw first. Again, see, I also got confused. The x is yaw, y is pitch, and then the roll. Okay, so just substitute in the matrix. Okay, so that the cos d that you see here is saying that we are taking an input as degree. Also, I will tell you how I define the matrix. So you the row entries are separated by space. Okay, and the column entries are separated by space, and the two rows are separated by the colon. Okay, then you get the matrix, and I just perform the multiplication. So you can put it in exam. I think you may have to do it by hand or some calculator, but here, okay, you can also see how it can be very easily done in MATLAB. And so if I run the section, get some value. Okay, and I think there are two minus signs over here. So let's go back to the MATLAB PowerPoint. Okay, so the second one is the answer. Okay, so let's move on to the next question. So the order that we multiplied here was this. Okay, uh, the question should mention the order actually. Okay, so now if a robotic manipulator possesses mechanisms to control all 6 degrees of freedom, then it is termed as. So this answer is holonomic. Yeah, but yeah, it's very again this question also holonomic usually means that you can instantaneously instantaneously move in all the directions. Okay, so in your space. So that is usually the holonomic thing. There is more mathematical definition also. Let's say if you have Q1, Q2, for those, so don't get confused, but those you who are have some mathematical background that they can say that if you have a constraint of this type where Q1, Q2, Q3 are generalized coordinates, then you can these are and all the constraints on the systems are holonomic, then the system is holonomic. Okay. Uh, Whereas if you have constraints which have this Q1 dot, Q2 dot, then it is non-holonomic. Okay. Uh, Also, for an intuition, we can say that, a omni-wheel robot, right? A omni-wheel robot with which has rollers on it, okay, can move in any direction, right? Any direction. So it is a holonomic system. Okay. Whereas a differential drive robot cannot move sideways instantaneously. It can go to this position, it can achieve this state when the state depends on the path it takes, and also it depends and it cannot be achieved instantaneously. So it is a non-autonomic system. So this kind of definition. Okay, then there is something called a redundant manipulator. So if you have more degrees of freedom than required to do the task, then we call it redundant manipulators. So let's say there is a robotic arm that has to pick up some object and then orient it in a particular direction. Let's say it has to pick up a laser pointer and point at some particular position in the slide. So so it has to achieve a certain 3 degree of freedom orientation and also a 3 degree of freedom position. So it requires 6 DOF, right? 6 degrees of freedom. But let's say that there are even more number of joints and positioned such a way that it can easily do this task, but it has more joints required to do than required to do this task. So such manipulators are there and they are built uh, because such manipulators can get into tight spaces, can move around the obstacles, right? Also they also mean that suppose a certain joint fails, still the task can be done. Okay, so that is the advantage of having redundancy. So snake can turn and go around an obstacle. Okay, and there it can do the manipulation. So for that, more joints are required than just six or something like that. So that is called redundant. Okay, but the answer for this particular question is holonomic. Okay, here I think to control all 6 degrees of freedom, so it means that control instantaneously. Okay, the meaning is instantaneous. Okay, so which of the following in the automation pentagon does a camera? So camera is a sensor, obviously you can. So sensor is something that senses or finds gets the information about the environment or about the robot. Actuator is something that makes the robot move, or it affects the changes the environment. Okay, so that is an actuator. Okay, so this is very simple and it's a theory question, so you can always look it up in the lecture slides. Okay, so let's coming back to the transformations. So there is this position sensor that has been attached to a wall. Okay, and it measures the position of a tip of the object after rotations with respect to the ground frame to be 548. So position sensor attached to the wall determines the position of the tip of the object with respect to the ground frame as 548. Okay, so this is the position with respect to the ground frame. So this is the fixed frame position, and there is some rotation matrix that has been done, and then we have to find the positionality of the object with its own reference frame. Okay, so we have to find this own reference frame, what is the position of that object, and the rotation matrix is done, performs a composite on a yaw, roll, and then pitch in that order with respect to the ground frame. Okay, so this is the rotations that have been performed with respect to the ground frame. So what is the first rotation that was performed? So it is yaw. So yaw is about x-axis, then this y, and then this is z. These were the rotations that were performed. Okay, and now if you see, let me pull up the matrix, MATLAB, and then I substitute. So this substitute the angles in those rotations, and what do we get as the answer? Okay, so okay, so again there is one more thing here. So the rotation matrix is with respect to the ground frame, right? So when do you say it's with respect to the ground frame? It means that this is this particular matrix only. RZ, RY, RX, and then this is PM, and this is PF. So what do we have to do? We have to take the inverse of this matrix to find PM. So we take the inverse of this, and how do we take the inverse? Just the transpose, and then you will get the into PF, and you will get PM. Okay, so let's do that, and so if I run this, you get 4 minus 2 minus 9. Okay, but take the inverse, you get minus 2, 5, and minus 8. Right, so the frame is also very much important. Okay, what is the frame? Okay, so as it was given, there was pi radians for yaw, and yaw was done first. Okay, then roll and then pitch. And a position sensor to the wall determine the tip after the rotations with respect to the ground frame. Okay, and to be 548. Okay, so these rotations were performed with respect to the ground frame, and after that you are getting the 548. Okay, and now what they are saying is find the position of the tip of the object with respect to its own frame of reference. Okay, so some water dripping down. Okay, fine. So so the answer that you should get over here is by taking the inverse of this and then multiplying with 548. Okay, so let's move on to the next question. Okay, find the homogeneous matrix and mark the statements that are true. Okay, so the given homogeneous matrix is this, and the x-axis of the fixed frame and that of the mobile frame are along in the same direction. So it is very straightforward to see that the x-axis of the fixed frame and the mobile frame are not in the same direction. Why? Because if they were in the same direction, right, then you would have gotten 1 over here, not -1, because this particular element has f1 dot m1, right? Okay, and similarly, so m1, if it was in the same direction, it should come +1, not -1, right? Why? Because cos of 0 is 1. Okay, whereas cos of pi, if they are in opposite direction, is -1. So they are in opposite direction, not in the same direction. So y-axis of the fixed frame and the mobile frame are along the same direction. Okay, so yes, it is true because it is +1 by the same logic. And the origins of the fixed frame and the mobile frame coincide. Okay, so if you see the position vector inside the homogeneous matrix, it is non-zero. It means that the origins are not coinciding, right? And the z-axis of the fixed frame and that of mobile frame are anti-parallel, means opposite. Let's see, yes, it is true. Okay, so if the position vector of a point in mobile frame is PM, then its position vector in the fixed frame will be PF. Okay, so and both PM and PF are given. Okay, and we have to find whether this is true. And to find that, what we should do is we should multiply the rotation matrix with PM and check whether we are getting this PF or not. So it's not rotation matrix, in this case it is homogeneous matrix. So you just take this homogeneous matrix and multiply with the given 0.540. Notice that this is a 3 cross 1 vector, so we have to append 1 at the end and make it 4 cross 1. Okay, and then you find that the answer that you get is 1.540. So again, there is a lot of typos over here. So this was given as 0.5, but actually what we get is 1.540. I'll show that in MATLAB also. Okay, and even in the previous questions, I find the answers not matching. Okay, for example, in this, not getting 0.45, I'm getting 0.35. And even in this particular question, yeah, there is some issue with the answer, or either there is issue with the answer, or whether where the the rotation order, the way they have mentioned, is not right. Okay, so we have to look into that. But I think in the current assignment, if you have the issue or you're not getting the answer, then you can tell. Okay, but this is the old assignment, but you can follow the method. Okay, and make sure direction of rotation is maintained, and uh, only then you can get the answer. And if you find that in none of the options is right, then you can put it in the forum and we will address the issue over there, or you can just mail us. So I will just write down my mail ID also over here, Suraj b@iitgn.ac.in. Okay. Uh, okay, and even in this particular question, okay, so the given answer in the previous year's assignment was wrong. Okay, this is the one which is correct. Okay, and as far as the other method that I showed you, where you figure out the rotations, it is not always easy to figure out the rotations. Because this was 90 degrees, we would try to figure out, and still I think we got it wrong. But if there are some other angles, then it becomes more difficult. So for some, if you are given some unit vectors, u1, u2, u3, and v1, v2, v3, then just go and take the dot product. Okay, that is the best method to deal with such issues. Okay, so we are done with all the questions. I will just show the MATLAB part uh, at the end, so that there is no confusion on how we for anyone. So it was a simple part only, but still someone might be new to MATLAB. Okay, so I didn't turn to the PowerPoint slide, so I will just repeat whatever I was talking for past 2 minutes. Right, so you are here, right? Yeah. So what we did was x-axis of the fixed frame and mobile frame, they are not aligned. If they were aligned, then the dot product would have come 1, f1 dot, because this particular element is f1 dot m1, right? And this particular element is f3 dot m3. This one is f2 dot m2, right? And whereas the y-axis, if you see, it is positive 1, so they are aligned. So the second option is right. Third option is wrong. The origins are not coinciding because there is a position vector which is non-zero. Okay, that is the reason. And for the fourth option, the z-axis of the frame and the mobile frame are anti-parallel. Yes, they are, because you can see there is a -1 over here. Okay. And as far as to verify the last one, you just have to multiply with this homogeneous matrix to the PM given and see whether you are getting PF or not. And you get, with this typo, 1.5 you'll get, right? And that's it. Very simple assignment with some confusion because of having this yaw pitch role reversed. Okay, Z is here roll and X is yaw. Okay, Y is pitch. Okay, so let's now go back to MATLAB. Uh, yeah. So just to show how we are defining a matrix. So if I want to, let's say, make some matrix of 1, 2, 3, 4, 5, 6, 7 in that order, then I will just have the elements separated by space for all the elements in the same row. And the next row, what I will do is I will first put the colon and then start entering the elements for the next row. And then similarly for the third row. Press enter and I get the matrix. So this particular area where I am entering is called the command window. Here you can test quick commands like this one. And this particular area where I wrote the code, This was the editor. So I can have multiple commands executed simultaneously, right? And here you can see the workspace where you can find the values of the individual elements. So as the course moves on, we will learn more such functions for those who are new to MATLAB. Okay. So I'm ending the session here. See you next Sunday. Okay. Bye.